In this video, we're going to talk about the relationship between equilibrium and thermodynamics. So from the previous video, we know that the free energy for a reaction at standard states can be calculated using this equation. So then we can just look at the appendix in the back of a textbook or find particular numbers for the delta G of formation online. And if we know the chemical reaction, we can use the stoichiometry of that reaction, so the stoichiometry of the balanced chemical reaction, to figure out the delta G at standard state conditions. But most of the time, reactions are not at standard state conditions. They're in some other state, a different temperature, a different pressure, for example. So how can we find delta G for systems that are not at standard state conditions or that are not at equilibrium? Because we know delta G at equilibrium is 0. So we learned previously in equilibrium chapter that when Q is less than K, the reaction proceeds forward. When Q is greater than K, the reaction proceeds in reverse. If we take this and we compare it to delta G, we know that a spontaneous reaction is a reaction that proceeds in the forward direction, and in that case, delta G of the reaction is less than 0. So therefore, in this case, Q must be less than K. For reactions that are spontaneous in the reverse direction, we know that delta G of the reaction is greater than 0. Therefore, Q must be greater than K. So from this, we can say that delta G of reaction depends both on the standard free energy, delta G naught, and on the concentration of reactants and products in the reaction mixture. So we can define the equation below: delta G at non-standard state conditions equals delta G at standard state conditions plus RT times the natural log of Q. At equilibrium, we know that Q equals K. Right? The equilibrium constant equals the reaction quotient, and we also know that delta G equals 0. So from the equation shown on the previous slide, if we substitute delta G for 0 because the reaction's at equilibrium, we end up with another equation: delta G naught equals minus RT times the natural log of K, or if we rearrange it, we can solve for the equilibrium constant. So this equation is useful because sometimes it's very difficult to determine equilibrium constants just by measuring concentrations of reactants and products. If a reaction is very product favored, then there won't be very many reactants remaining, and it might be very difficult to measure concentrations of reactant. On the other hand, if a reaction is very reactant favored, then there will be very few products to measure concentrations of, and again, we may not be able to do that because the concentrations are so low. So instead, if we know the delta G at standard state conditions, we can calculate equilibrium constants using this equation rather than what we've learned in previous chapters. So if we look at this particular reaction, N2O4 in equilibrium with 2NO2, it has a standard state delta G of 4.8 kilojoules. So that means at standard state conditions, this reaction does not proceed in the forward direction. It would proceed spontaneously in the reverse direction. Now, if we compare this to our discussion previously on Q and K, remember when Q is less than K, the reaction proceeds to the right. That's when we only have reactants. So that's when we are right there on this curve, the first circle, condition 1. And the reaction always wants to go towards the minimum energy. So it's like rolling a ball down a hill. The reaction wants to go in the forward direction, so towards the right, to achieve equilibrium. Now, if we have only products up here in condition 2, Q is larger than K, and the reaction has to proceed to the left in order to reach equilibrium, right? So the reaction has to proceed this way, starting from condition 2. It has to proceed this way to the right, starting from condition 1. So on this graph, the reaction would want to proceed to the left in order to reach equilibrium. And if the reaction is at equilibrium, then we're at condition 3, where the reaction has already reached the minimum energy. So the reaction has nowhere to go. It can't go to the right and it can't go to the left. So let's relate this back to our equilibrium chapter. So if we have an equilibrium constant that is much greater than 1, we know that this reaction is product favored, so at equilibrium there will be more products than there are reactants. When we're talking about thermodynamics, that means that delta G is going to be less than 0. And if you remember these energy diagrams from previous chapters, remember that because the activation energy is smaller in the forward direction than it is in the reverse direction, that means that the reaction is going to be product favored. Okay, so again, at equilibrium, there will be a higher concentration of products than there are reactants. So if we had an equilibrium constant that was slightly greater than 1, so it is still going to be product favored. We're still going to have a delta G that is slightly negative, or less than 0, but at equilibrium, the reaction won't be highly product favored, it will only be slightly product favored. And again, if we look at the energy diagram, we can see that the activation energy for the forward reaction is just slightly larger than the activation energy for the reverse reaction. Now, if we have an equilibrium constant that is much less than 1, that means the reaction is reactant favored. And if the reaction is reactant favored, then delta G naught is going to be greater than 0. A positive delta G means the reaction is spontaneous in the reverse direction. And from our energy diagram, we can see that the activation energy for the forward reaction is a lot greater than the activation energy for the reverse reaction. So the reverse reaction is going to be the spontaneous reaction in this case, and we're going to have more reactants than products at equilibrium. So let's just go through a quick calculation and determine the equilibrium constant and delta G of formation for this particular reaction. So the first step is going to be to determine the delta G at standard state conditions. And we know how to do that. We use this equation right here. And we're given the information, the delta G of formation for each of the reactants and products, so we can easily figure out what the delta G of reaction is at standard state conditions. So if we fill in the numbers, we end up getting a delta G of reaction at standard state conditions of minus 41 kilojoules per mole. Now the second part of the question asks us to find the equilibrium constant. So we can use the equation from a previous slide to calculate the equilibrium constant. And the thing to be aware of is that delta G, as we calculated, was in kilojoules per mole, but we need to have it in joules per mole in our equation. And the reason for that is the constant, 8.314, is also in joules. So make sure to make that conversion, otherwise you're not going to get the right answer. So solving for K, we end up getting 1.54 times 10 to the 7. So now let's quickly talk about the influence of temperature on the equilibrium constant. So we know at equilibrium, delta G naught equals minus RT times the natural log of the equilibrium constant. And we also know that delta G equals delta H minus T delta S. So we can make minus RT natural log K equal to delta H minus T delta S, do a little bit of rearrangement, and that gets us to a point where we have the equation of a straight line. So natural log of K is Y, minus delta H over Y is M, 1 over T is X, and the delta S over R is B. So if we were to plot the equilibrium constant versus the temperature, we would end up with a straight line where the slope is minus delta H over R, the intercept is delta S over R, and from this we could calculate or determine what the delta H of the reaction is and what the delta S of the reaction is. Now, another way we can determine what equilibrium constants are at different temperatures is to use the Van't Hoff equation. So if we know the equilibrium constant at one temperature, we can find the equilibrium constant at another temperature. So notice that this is very similar to the Clausius-Clapeyron equation that you learned about previously. So let's just go through a quick example of the Van't Hoff equation. So at 2000 degrees Celsius, the value of the equilibrium constant for this reaction is 4.1 times 10 to the minus 4. What is the value of K at 75 degrees Celsius if delta H equals 180.6 kilojoules? So we know we're going to use the Van't Hoff equation. And now all we have to do is fill in the equation with the appropriate values. And again, since we are given kilojoules for delta H and our constant is in joules, we have to make sure that the delta H in the equation is given in joules. So the other thing to be aware of is to make sure that K1 and K2 are in the right part of the equation and T1 and T2 are in the right part of the equation. So the K value for K1 has to correspond to temperature 1 and equilibrium constant K2 has to correspond to T2. So now we can just solve for the right-hand side of the equation because all we have over there is a bunch of numbers and we end up getting what we see here. Now to get rid of the natural log, all we have to do is take the inverse natural log of both sides of the equation. So that cancels out the natural log on the left-hand side and we have e to the minus 52.86 on the right-hand side. All we have to do now is rearrange the equation, solve for K2, and we end up with a number of 4.51 times 10 to the minus 27. That's all I have for this video. If you have any questions, please feel free to ask.